and announcing the following talk is a special pleasure for me for two reasons. One is it's colleagues from ENW. And second, as a conference organizer, I think in a track which is populated heavily, say, by people from corporate organizations, you have to have a cool cube talk. That's like from planning and scrabbling, there must be one. And so this is the one. Lorraine, Sven, go ahead.
All right, thank you. And yeah, hello, welcome everyone to our talk. Today we want to show you how we broke multi-tenancy in Kubernetes in multiple ways and show you what we can learn from it. How many slides?
Oh, yeah, it would be good to... yeah, we have also slides here.
Yeah. Okay, so before we start, who we are. Yeah, my name is Lorraine, and this is my colleague Sven. We both work as a security analyst at the company ENW. I work in IT security since 2019 as a pen tester and security researcher. I've been recently focusing on cloud and Kubernetes security. I've also done a few Kubernetes workshops. Yeah, I'm also an active member of the Black Hoodie community, and I mentor newcomers. So for those of you who don't know Black Hoodie is a women-only organization for basically all women who are interested in security. And I also help organize Black Hoodie workshops at Troopers. And if you want to ask me anything besides security, then I can talk about plants for hours, especially olives.
Yeah. A little bit about myself. I started my career nearly 20 years ago as an IT professional. I started as a software engineer. Nowadays, I wouldn't call myself a software engineer anymore because I switched a long time ago to cybersecurity, and I'm a pen tester at Retima, security researcher and trainer and consultant. I've seen Kubernetes and cloud to grow up, especially in terms of security. When Kubernetes started, there was nearly no security involved. Nowadays, there's a lot of development there, and that's the reason we also want to talk about today. If you want to talk to me something else than security, I'm a coffee nerd like many IT guys, and outside of my daily work, I'm an improviser on theater stage, sometimes also during my work days. Back to you, Lorraine.
Yeah, here in the background, you can also see the rest of our team. Yeah, so in our today's agenda, first we want to talk about what is Kubernetes, what is multi-tenancy in Kubernetes. Then we want to show you how we broke multi-tenancy in Kubernetes in different ways. And then we want to show you our methodology we developed to help mitigate these issues. And lastly, conclusion with some takeaways. So let's start. What is Kubernetes and why Kubernetes was born? And to understand the need of Kubernetes, first we want to have a look at the containerized environment. Yeah, so as we all know, containers are more lightweight and they take less resources in compared to virtualized environments. And here we see that the application and its dependencies all live in a container, and containers all share one operating system. So now we need to efficiently schedule those containers on the available resources we have, to fully utilize them. And this is an impossible task to do manually, especially if you consider hardware might fail. So as an operator, you ask yourself, how can I manage all those workloads? And here comes Kubernetes in play. So Kubernetes is an open source container platform which does more than orchestration. So what does this mean? Now as an operator, I can tell the control plane, this is my workload that I want to run in the cluster, and this is how they should be configured, and the control plane take care of scheduling these workloads, including where those workloads should run in. And Kubernetes does more than that. They also take care of scaling and also take care of the resources in case of failure. So nodes here represent also, can represent a virtual machine or a physical machine. And you've probably noticed that the container here is wrapped up with another box called a pod. What is a pod? We need to do some basics Kubernetes first. So a pod is a Kubernetes object, or in the Kubernetes terminology, it's called a Kubernetes resource. A pod can contain one container or multiple containers where our application runs. And in Kubernetes, you can represent any pod via a YAML file. And we would see a lot of YAML files today to explain our exploit, so they're quite important. So here's a sample YAML file which represents a sample configuration of a pod. So here we see that the pod name is Nginx, and it has one container configured, which has the name Nginx, and uses the Nginx image and expose the port 80 where our Nginx application is running. So a pod is one kind of Kubernetes resource, but we have a lot of other kinds of Kubernetes resource. A service exposes an application and uses labeling to reference the target pod. We also have namespace in Kubernetes. This is quite important. We'll talk about it a lot today. But there are also other resources in Kubernetes. All of these resources that we've just seen are built in Kubernetes resources. So standard Kubernetes resource, you will find them available in any Kubernetes cluster. But there are also custom resource definitions called CRDs. They extend Kubernetes, and there are a lot of projects that does that. A few of them we'll talk about today. So we just mentioned namespace is important. Let's see what namespaces are in Kubernetes. So with the help of namespaces, we can organize our resources in the cluster. As an example, we can have team A and team B. We want to give our tenants or teams access to the cluster where each tenant can execute their own workloads, and we want to isolate these workloads from each other, so we can do this via namespaces in Kubernetes. This is one way to implement multi-tenancy in Kubernetes. Okay, so we talked a bit about theory for now. Now let's see where we come from and why we did our research. As the security researchers, and as security fantasists, we worked with different customers in different sectors, and we have seen that namespace-based multi-tenancy is quite often used, and it is challenging to harden from the security perspective. So we decided to do a research with the question, is industry best practice hardening enough to isolate namespace-based multi-tenancy? And the answer was, okay, we found many problems which are not well studied yet. So let's dig into the breaking part now. What is namespace-based multi-tenancy? Here on the right side, we have a simple cluster where we have tenant A have access to namespace A, and tenant B have access to namespace B, and all tenants share one cluster. And we notice here the dashed line and the straight line. So the dashed line represents the communication or the control plane or communications for managing the cluster, for example, to interact with the Kubernetes API. And on the data plane level, this represents communications between workloads that our tenants, for example, deploy in the cluster. And what we found that there are many ways to break such isolation, and the current security best practices do not protect against these problems. So today we want to show you 3 exploits that we found, 2 on the control plane layer and 1 on the data plane layer. So let's start with the first exploit, breaking multi-tenancy via insecure cross-namespace references in custom resource definitions, or CRDs. What are cross-namespace references? Here we have a simple cluster where on the one hand we have namespace 1. The namespace 1 have one resource, as we just learned that we can represent resources also via YAML file. And the kind of the resource is target CRD with the name example. On the other hand, we have another namespace, custom resource definition. And what we notice here is that this resource reference another resource from a different namespace. So why is this a problem? And to understand this, we introduce our first real-world scenario in Kubeflow. First of all, what is Kubeflow? Kubeflow is a CNCF project. For those of you who don't know what is a CNCF, CNCF stands for Cloud Native Computing Foundation. It's an organization which hosts major open source cloud native technologies, and Kubeflow is one of them. Maybe shortly. So Kubeflow also offers a machine learning and AI platform on Kubernetes. Let's have a look at the Kubeflow dashboard now. What does it do? So, as a user, I have from Kubeflow a Kubeflow profile assigned. The Kubeflow profile here is assigned to a namespace in Kubernetes. And this is a classical namespace-based multi-tenancy we see here. So a user on the Kubeflow dashboard can create now their own machine learning workloads through pipelines and notebooks. And they can execute workloads within these. So let's click here on Connect and have a look at the notebook, or the Jupyter's notebook here, that the user have access to. And with the security mindset, okay, we want to see, there's a terminal from the Jupyter notebook, like to see what can I do with it. No? So let's have a deeper look at the terminal here. So the first thing I want to see, okay, what can I do here? What permissions do I have, and so on. So in Kubernetes, we can use the command line tool kubectl to interact with the Kubernetes resources in the cluster. So we use that. kubectl auth who am I to see, okay, who am I in the cluster? And we see that we have a service account assigned to our users, which is called the default editor. Okay, this is interesting. But now we want to see, okay, what permissions does this service account has? And we can do this via the command line kubectl auth cani --list. So I list the permissions here. And I see quite some well-known permissions, like the config maps and deployments. But what is also interesting is the user has also permissions from Istio. And the user can, for example, create virtual services. This is interesting. Let's find out why. But first, what is virtual services? Here we have a simple cluster where we have a request coming from the outside of the cluster. It goes first through the load balancer. The load balancer then forwards a request to the Istio gateway. We notice here that the Istio gateway exists in the gateway namespace. And the Istio gateway then routes the traffic to the virtual service. The virtual service here exists in the workload namespace, in a different namespace than the Istio gateway. And the virtual service then forwards a request to the pod. So important here, the virtual service exists in the workload namespace where the user also have access to. Okay, now we learned what is virtual service. Now let's go back to our example from earlier and now apply the virtual service resource we just learned. Now we have, on the one hand, the Kubeflow namespace, where the gateway resource exists. On the other hand, we have the attacker's namespace, or the user's namespace. And we just learned that they can create a virtual service resource. And what they can do now, they can reference the Kubeflow gateway, which exists in a different namespace. Okay, what is the problem here? And to understand this, we introduce now our attacker. And our attacker goes as follows. They can create their own virtual service now in their namespace. And they can reference the Kubeflow gateway, which exists in a different namespace. They override now the Kubeflow fev icon with their own chosen fev icon, and override or route the request to their own controlled pod. Now we look at on top at the Kubeflow dashboard again, and what we notice here is that the fev icon of the Kubeflow dashboard has been overwritten with the chosen attacker's fev icon. This is interesting, but I don't know the security impact of it yet. So to understand that, let's have a look again what we just did. We have on the one hand the Kubeflow user who is accessing the Kubeflow dashboard, and as we just learned, this request is then forwarded to the attacker's pod through the Kubeflow gateway. Now what the attacker can do, the attacker can log these requests, they have access to it, and within these requests, they also have access to the Kubeflow sessions cookie. So they can impersonate that Kubeflow user and can do anything on their account, basically. This also, of course, applies to any Kubeflow user who's accessing the Kubeflow dashboard. This is a problem. Now let's move on to the demo time, and for that I will give Ben.
Thank you, Loreen. So we've seen that in theory. Let's show it that this exploit also works in the real world. And for that, I change to my two browsers. So on the left side, we have the blue browser with the victim. On the right side, we have the attacker's browser with the red, with the red window. So let's log in as a user first and show what the user does in his daily work. So we sign in as victim.inaw.eu. Here's an account in Kubeflow, and I will make the window big now. And you can see here, he has only access to his victim namespace. Or they have only access to the victim namespace. They have created in a notebook, and when I connect to the notebook, we can see here the victim works with some very sensitive data. So you have all the employee passwords, and this, I will not show them, this should be protected. So the attacker wants to get access to that. So let's try to do that. We will switch over to the attacker. We sign in with the attacker's account. He has also an account in Kubeflow. Attacker.inaw.eu. We log in, and I will also make this window big now. So he has only access to the attacker namespace or attacker profile. He also created in notebook, and when we connect to that, we see he has prepared the attack. This is something Loreen already showed. He created a virtual service, and it's deployed to the Kubeflow gateway, and we override the fev icon and route it to the attacker-controlled pod. We have a few other resources below so that the attack works. For instance, we have a deployment here which creates the pod where the traffic is routed through, and this pod runs an image with a small HTTP server written in Go, and every time a request is made to the fev icon, we dump the complete request to the console. And the console output is forwarded to kubectl logs, so we can later look at the requests made to the web server. So let's deploy this attack. So we use kubectl, apply, -f, and deploy it to the cluster. So we can see here our virtual service is created. Also the deployment with the pod is created. And then we have deployed this attack. There's one thing Loreen omitted until now, because our attack won't work until yet, because we have one detail which we didn't talk about yet. There are authorization policies in place in Istio. You can deploy authorization policies to define who can access network-wise the resources of the attacker's namespace. And at the moment, Kubeflow as in default applied that nobody else than the attacker can access the attacker's namespace. Otherwise, everyone else would be able to access this notebook you're running. So we need to find a way to allow other users to access the attacker's namespace, to access the fav icon resource, to access the virtual service. And we don't have the permission to edit these authorization policies. So yeah, will this attack not work? No. We found a way to bypass it, and this is pretty interesting because we can manage in our contributors in our own namespace and say who has access to our namespace. And we might not know who you want to attack. We want to attack all of the Kubeflow users might be. So we can even use an asterisk and say everyone from ENW is a contributor of this project. Oh. It didn't reload. Maybe the network is not so fine here. So now we have authorized everyone from ENW.eu to access the attacker's namespace. And the cool side catch about this is that they even don't see that they have access to this namespace because of the asterisk. This is a bug, and you cannot see it here. Otherwise, we won't see it. But if I use the asterisk, the victim, we won't see it. So we have prepared everything for our attack. We already see here in the attacker's notebook that the fav icon changed. But did it also change for the victim? So the victim accesses the dashboard again, and we see we have the red icon here. That's nice. So let's impersonate the victim's account as an attacker. So I switch back to the attacker and go to the Jupyter notebook from the attacker and say kubectl logs, and then I choose the deployment, service POC. Next time I use a shorter name. And take a look at the logs. We see some health checks here done by Kubernetes, but we also seen that there was a request to the fav icon. And we see the whole HTTP request in our logs, and also that it was made by the victim. And what you can see here, here's the cookie we are interested in, and with that we cannot impersonate the victim's account. So I will start a new session, go to the Kubeflow dashboard, and set in the developer tools the cookie of the victim. So I first copy the name of the cookie. Put it in, and then cookie. Then I enter the cookie, and if I refresh the site, I have access to the victim's account. So wait a second, I didn't show the confidential data yet. So, and we also have access to the confidential data. And as an attacker, I can show you the passwords. They're very secure. And for that, I will go back to the slides and give back to Loreen.
Yeah, this is an issue. We did a coordinated disclosure together with Kubeflow, and Kubeflow fixed this issue by removing the issue edit permissions from the service account. And at this point, we'd also like to thank Kubeflow for fixing this issue in a timely manner. Yeah, insecure cross-namespace references in CRDs is a common problem, and they exist in various other projects, not only in Kubeflow. And there is an excellent research paper that was released last year, so shortly before we finished our research, actually. After we finished our research. So they explain that this issue exists in a lot of other projects as well. So it is pretty common. Okay, so now we are at the end of our first exploit. Now let's move on to the next exploit and show you how we broke multi-tenancy again, and this time via annotations. So, first of all, what is cross-namespace references and annotations? Here we have a simple cluster again. We have two namespaces in the cluster, and what we notice that on the one hand, the service resource references via annotations another resource which exists in a different namespace. And this time is the referencing resource a built-in Kubernetes resource. And as we've learned, this is problematic, and to understand now why or what is the impact of it, we introduce now our second real-world scenario, this time in traffic. And traffic, for those of you who don't know, is a popular open-source HTTP reverse proxy and load balancer. Let's have a quick look how traffic works first. So if we have a request coming from the outside of the cluster, it goes first to the traffic's proxy, and the traffic proxy then forwards the request to the service within the cluster via ingress. Ingress is not shown here just for simplicity, yeah. And then the service forwards the request to the destination pod. What we notice here is within the service resource, we can, via annotation, reference a service transport. What is a service transport? Service transport is a custom resource definition from traffic, and it tells us or configures how traffic connects to the destination service, in this case via mutual TLS authentication. Okay, now we know the example. Now, what is the impact of this? And to understand that, we introduce again our attacker, and we keep only the relevant resources in the cluster for now. So now we have the victim's namespace, where it exists in the victim's namespace, the service transport resource, and the victim has also a pod deployed in his own namespace, in their own namespace. Now we introduce the attacker, and the attacker exists in their own namespace, and they have permission to create a service resource in their own namespace. Now, what the attacker can do, they can, via annotation, reference the service transport of the victims, which exists in the victim's namespace. And now, the attacker can use the traffic's proxy to do the mutual TLS authentication for them, forward the request to their own controlled SOCAT pod, and then to the destination pod. So the attacker here uses the client certificate of the victims, which exist in the victim's namespace, and the attacker has no direct access to this resource, but still can use it. So yeah, this is a problem. We have done here a coordinated disclosure also together with Traffic. Traffic is currently fixing this issue. However, they updated already their security documentation in regards of multi-tenancy, and they recommend using the Gateway API. At this point, we'd also like to thank Traffic Project and the maintainers for the great cooperation with them. We learned also a lot on the way. Insecure cross-namespace references in annotations is a general problem, and their security impact goes even beyond the scope of the cluster. And to understand that, we brought here a simple example of an ingress resource. So if you now give your tenant the permission to create their own ingress resource in the cluster, they can, via annotation, reference any compute certificate which is defined on the GCP cloud provider level. So the impact of it goes even beyond the resources of the cluster, but on the cloud provider level. Yeah, this is also problematic. So now we're at the end of the second exploit, and now let's show you how we broke multi-tenancy again and again, and this time on the data plane level. And for that, I will hand over to Sven back.
Thank you very much, Florine. As a quick side note to this annotation problem, we had just our Kubernetes workshop last 2 days, and I found an unintended security bug in our lab setup because there's also such kind of a problem with the annotations, because everyone could create DNS names through annotations in ingress, and those could deploy any DNS name through external DNS in our lab setup. This is not a problem because I could get cluster admin anyways, but it was not an intended bug. So this is a common problem we even found in our setups. So let's move over to the data plane, and for that I will go back to our friend Istio and its service mesh. And before I come to the vulnerability, I quickly explain what the service mesh is, what we need to know to understand the attack. And on the left side, we have our cluster with the victim namespace, and there's a workload container running. And this workload container makes requests to the service mesh and also to the internet. And the interesting thing about Istio is there are two ways to implement the service mesh, the ambient mode and the sidecar mode. We're focusing here on the sidecar mode, but this works also in the ambient mode as in side node. And we have a workload container here, and if a request is made to the sidecar, it's routed to this. If a request is made to example.com, it's first routed to the Istio sidecar. And the Istio sidecar then decides what to do with the request. Is it a request for the service mesh, or is it a request to the internet? In this case, it's a request to the internet to example.com. So it's sent to the example.com until our attacker comes into play. So he has his own namespace, and he deploys a virtual service. But this is a special kind of virtual service. And why is that a problem? Because it's a virtual service deploying something on the service mesh. So there is a gateway below, and it says service mesh, and this is a special kind of virtual service. And then the attacker says, I'm host example.com. And now, if the workload container wants to request something on example.com, it will be forwarded to the sidecar, as we know. And the sidecar sees, there is example.com is on the service mesh. I will route the traffic to the attacker-controlled pod then. And the attacker can now intercept the request to example.com. And this is a classic man-in-the-middle attack. There are some limitations about this man-in-the-middle attack. He can intercept any request, even any request to any pod or any service in the service mesh. So it's not only destinations in the internet, it's also destinations in the service mesh. He can intercept them. But if he wants to forward this request to the original service, to the destination service, he needs to have access to the destination service. So the authorization policy needs to permit the attacker to access those destination services. So if you want to capture the traffic between the two services. The second side note about this thing is that the destination service sees that the request originates from attacker namespace, not the victim's namespace. But this is in many cases not a problem to perform a man-in-the-middle attack and gain access to interesting or confidential data, but it's a small limitation. We also did a coordinate disclosure together with Istio. Istio maintainers consider this issue expected behavior. It's a proposed user trade-off because these APIs were designed before airbag in Kubernetes even exists. I mentioned in the introduction that Kubernetes was very insecure at the beginning. They didn't even have airbag at the beginning, and Istio were designed at this moment. So they don't want to break existing setups. So they say, okay, if you have namespace-based multi-tenancy, don't use the virtual service APIs anymore. Migrate to the gateway API like Traffic did, and because they provide a secure way to do cross-namespace references. It's also a thing we would recommend. So if you be able to use gateway API instead of the Istio APIs, instead of the Traffic APIs, instead of Ingress, use gateway APIs because they designed these APIs with security in mind. They're really pretty new, but have a secure design behind it. To address this issue, because it was not known before, we published a security note and a blog post together with Istio. And thanks to the Istio project to give us this opportunity to inform the community about the security problems and that everybody can learn from it and improve their security. So I hope we learn now what we can learn from it. So let's move over to the last part of our talk, the methodology. We have developed a 3-step methodology to find these problems and similar problems in your clusters. So the first step of the methodology is the use. Do I use namespace multi-tenancy? The second step is the assess step. If I use namespace multi-tenancy, how do I identify potential weaknesses in my cluster? The third step is the address step. How do I address them if I have those weaknesses? Let's come to the first step. Do I use namespace multi-tenancy? And to answer that, where's namespace multi-tenancy commonly found? And you might think, I know that I have namespace multi-tenancy, or I know I don't have it. But it's sometimes not so easy to answer. So the first example is a pretty easy example you might think of. We have multiple teams. Lauren already said it during the introduction. We have team A, team B. Everybody has access to their own namespace. They deploy their applications into the cluster. And you typically share a level of trust with your teams. You trust your teams that they do not harmful stuff, and you have the security and control in your company. So yeah, attacks are pretty rare. The severity or the probability that this happens is not so high. But we have a second example where the probability is a lot higher. We have multiple actors, often customers, sometimes even random users from the internet who can register to your applications or to your solutions, and you give them access also to your cluster. Often this is only indirect access. So we have a few examples here. Machine learning, we've seen this with Kubeflow. Everybody who can use Kubeflow can deploy resources to the cluster or run workloads in the cluster. And also another example is CI/CD pipelines. If you have it in your company, there might be a production deployment which has credentials to access a production and to deploy something with production deployments, which are pretty critical. But we also have this typical pull request pipelines where you check if the code is running before it gets into the master branch merged. And this is typically not so risky to have it because you trust your teams, but there are even examples, if you use github.com, that public users from the internet can trigger those pipelines. Trivy fell in that pit a few months ago, and there was big slash about this because somebody compromised the Trivy deployment, and everybody who was using Trivy got also his pipelines compromised. So this can be pretty critical. Other examples are scripting capabilities and applications. We come to that in the moment. And this access is typically untrusted. You don't trust a random user from the internet. Also, don't trust fully your customers because you don't control the security of your customers. And it's also sometimes unrealistic that you have multi-tenancy. And to explain that, I will first define what is unrealistic namespace multi-tenancy. Tenants are hidden in the deployed applications and workloads that implement features which give tenants access to the underlying platform. What does this mean? So if you take an architecture diagram of your applications, you might not see that you have namespace-based multi-tenancy, or even worse, workload-based multi-tenancy. So, and the users of your platform application can access certain features of the Kubernetes platform. This can be through various ways. We see with Kubeflow to code execution, so you have access to the data plane and access to run code in the cluster in some workloads, or even can access the network data plane, like can access the service mesh, for instance, through server-side request forgery. This can be intended server-side request forgery, or through other things like files and other stuff. Or you have even access to the control plane through the Kubernetes API. And this can be also sometimes very onerous that you have it, because you don't need, in all cases, give the customer or the tenant access to the Kubernetes API. As we've seen in our Kubeflow example, if you deploy a new notebook or a new pipeline, there are a lot of resources created in the background in the cluster. And nowadays in cloud-native applications, it's the case that the application does something. The user uploads a file, user does something, run a script. In the background, new Kubernetes resources are deployed. So the attacker has some control of resources in the cluster and might be able to interact limited to the Kubernetes API. I have some example of unrealistic namespace multi-tenancy here with ChatGPT. On the right side, I have some example I ran a few years ago when they introduced a new Python scripting feature. And it's base 64 encoded because at this time, ChatGPT didn't want that we run code, run OS commands. You can only run Python code, so I obfuscated it and asked, please print the environment variables to the console. And so that I get the output and it's not omitted. I also basically 64 encoded it, and if we decode it, we see that the ChatGPT's Python sandbox runs in a Kubernetes cluster. So we have either namespace multi-tenancy here or even workload-based namespace multi-tenancy here. So this is a pretty interesting example, and you can dig around, especially the feature where you can use the agent mode, where we have a browser which is controlled by ChatGPT is interesting because you have network access there and code access to 2 containers, which are runs in a namespace. So they have unrest namespace multi-tenancy because when you run the agent mode, in this case, you have access to a namespace and to multiple resources there. Pretty interesting as a research topic. Yeah. So now we know that we have namespace multi-tenancy, even if we didn't think about it at first. And then we need to identify if we have potential weaknesses. First of all, we assume that you already applied industry best practices. So you applied hardening like pod security standards, applied network policy, and other known stuff that you harden your cluster against the security best practices. After that, you need to identify all components which are in control of a tenant. What can a tenant do in your cluster? Run code, access a network, or even deploy Kubernetes resources. If I know what components are in control and which resources are in control of a tenant, I need to assess those resources. What control plane interaction is with these resources possible, and what data plane interaction is with those resources possible. If I know that, I need to evaluate the interactions and ask myself, does this affect the security of components outside of the namespace? So, does it affect the confidentiality? Can I access the confidentiality? Can I bypass, can I access the confidentiality of components outside of my own namespace, the integrity or the validity? And this is sometimes not so easy to answer because, for instance, availability is often hard to answer because every time I can do something in the cluster, this might affect the availability because if I can deploy a lot of resources, I can exhaust the available resources, available compute resources, available network resources. And so these interactions are not so easy to evaluate and to determine if there is an impact on the security. If I know I have an impact, I need to address them. First of all, I can do like we did with Kubeflow, with traffic. We can report the issue, and they can deploy a fix for that issue. This is pretty easy. I can apply the patch, and I'm safe now, but this is not always possible. We've seen that with Istio, so there's no fix available. And in that case, I can try to use existing admission policy sets, which restricts the capabilities of a tenant, which restricts what a tenant can do. And there's, for instance, an excellent repository if you use Kyverno. They have a lot of policies which present this kind of issues for different problems. But this is not always a suitable solution because you have, there might be not an available policy, or you have very specific problems, and then you need to develop your own custom policy. And I have an example on the next slide with an example admission control policy. So we have here back our virtual service. And if I want to allow my tenants to deploy a virtual service, but in a safe way, I can do one of the 2 things. First of all, I can say the tenant can deploy virtual services, but only on specific gateways. He's not allowed to deploy something on the service mesh. He's also not allowed to deploy gateways, virtual services on gateways of another tenant. He's only allowed to use his own gateways in his own namespace. But this might be not a solution for you because you say, okay, my tenants should be communicating with each other, and I want to use the service mesh. Otherwise, I don't need the service mesh for that. And then I can restrict the host section and say a tenant is not allowed to override any host with the asterisk, or not allowed to deploy a virtual service which overrides a host in the internet or a host of another tenant in the service mesh. He's only allowed to use to deploy services on a specific domain which is assigned to this namespace, and then I can give them safe access to the virtual service kind of resource. This is also the end of a methodology section, and I would like to conclude the talk with some takeaways. So I would like to increase awareness. We would like to increase awareness. So namespace multi-tenancy is hard to get right. I hope you've seen that during our talk. And also its presence might be onerous. I hope you've seen that too during our talk. So invest your time to assess its implication if you have it. And you can use our methodology as a guideline to assess your clusters. We have published our methodology in much more details on GitHub. You can scan this QR code or use the link below to go to that and then do an assessment of your own clusters. And with that, I want to thank you for your attention. If you want to talk more about security with us, you can reach us through mail or through LinkedIn. Also, we are still here. Talk to us after the talk. And we could not show all problems today in the short time. And also, we have much more details. We published a few blog posts on our blog, incinerator.net. You can follow the blog, and we will also publish a few more coming soon. And I think we have still a couple of minutes for questions. So thank you again.
Yeah, actually, we do have time for some questions. So, any questions from the audience? None of them. Last chance. Okay, there's one.
In the first example, you show that you are running kubectl on a Jupyter container that probably doesn't come installed in a normal image of a Jupyter. How did you get that one installed?
So this is what we've shown is a standard kubeflow setup. And in a standard kubeflow setup, the tenant or the user gets access, has a service account attached to his Jupyter notebooks, automatically attached. And also in the pipelines, there is a service account attached. This is also necessary to have the service account because kubeflow is a cloud-native machine learning platform, and they utilize a lot of features from Kubernetes. For instance, you can create volumes to store your data and also access other resources through the Kubernetes API. So it's necessary to have them, but it wasn't necessary to have the virtual service permission. But this is still a risky part to give them access to the Kubernetes API because they can, in default, for instance, also deploy their own pods. And if you don't have pod security standards applied, then you can also deploy privileged pods and so on. So it's hard to get right in this case to make it secure.
Any other questions? If none, thanks again.
There's the question.
Sorry for that. Looking in the right direction. Here we go. Thank you.
First of all, thank you for the talk, and the presentation was very interesting. Usually when my boss comes to me and say something about new vulnerabilities or weaknesses, I have to do threat hunting. And do you have any evidence or information about how to see if somebody did this in the past in an environment?
That's a good question. I mean, from a general perspective, there is this CNAPP platforms where you cloud-native application security platforms where you can have observability in your cluster. What does happen? And for the first vulnerabilities, we've seen that we deploy new resources, and I think there's no. You have audit logs, what happens, but none of the audit log would show at the moment that somebody did this because this unknown vulnerability. So if you see that there is a fix, there was a vulnerability for the components you're using, and you apply the fix, you can look for the specific issue in the logs if somebody referenced via annotations or via a reference did this stuff, and then you can see if such kind of attack happens. For the data plane thing, you have the network log, flow logs, and then you can look for unusual traffic. So normally, the attacker's pod should never communicate in such a way, as such a flow shouldn't happen. But it's also not that the platform itself will show it to you because this kind of attacks are unknown yet. But if you know that you have this kind of problems, you can dig for this kind of problems if somebody used this exploit chain.
Okay, maybe, hopefully I don't miss anybody right now. Thank you, Doreen and Sven.